Today we're going to be looking at this step question from the step 3 paper from 2013. So this is a statistics question. So there's lots of stuff about ideas about probability and expectation values. And as you can see, integration comes up a little bit. And there's a few inequalities towards the end. So starting off, what do we have? So the continuous random variable x satisfies x between 0 and 1 and has a PDF of f of x and CDF of big F of x. The greatest value of the PDF is m, and then show that the cumulative distribution function is between 0 and mx for x between 0 and 1. So this first part here, I guess all we need to do to show this is we could just use a diagram, I think. So we can draw like any arbitrary probability density function here. And we know it's defined between 0 and 1, so at 0, that's 1. And the area underneath this curve is going to be the cumulative distribution function. So let's keep that in mind. Now, what do we have? We have this statement here. The greatest value of this function is m. So if we say this point here is m. Okay. Now, if you think about sort of what the cumulative distribution function means. This means that the integral between 0 and x of the PDF is going to be that area underneath the curve here. So this is what f of x is referring to. So if you want to think about this sort of inequality, so this area under this curve is always going to be smaller or equal to than this rectangle created by the maximum value. So as such, we could say f of x is less than or equal to mx, because mx is that rectangle and f of x is just the area under the curve. Now, for the lower bound, we can see that if the probability density function was literally just like, on the real axis, then there'll be no area underneath. So you can say it's lower bounded by 0. So yeah, that's that part. Now we have something that's completely different. For any function g of x, show that, and then this integral thing. So you can kind of see straight away that this kind of looks like integration by parts. We have this g of 1 thing here going on. Then we've got this like g prime of x, and then looks like this like vaguely integrates to that. So let's get started with that. Now, yeah, I'm gonna reiterate what we said about the CDF. So the CDF in our case is the integral between 0 and x of f of t dt. So what this means by the fundamental theorem of calculus, that f prime of x equals f of x. So we can use this when we're integrating. So if we write our integral down, we have the integral between 0 and 1 to g of x, and then we have f of x and the other f of x. So if we wanted to use integration by parts here, we saw that we wanted to end up with some sort of g prime of x. So we set the equal to what we're differentiating. So we say u equals g of x, and then we see that that constant term out front, that 2 over here, sort of doesn't stay outside, so it's probably used up in the integration. So we say v prime would be 2 big F of x, little f of x. Now we can work with this. So we have u prime is g prime of x, and then integrating that, we can see that since we said earlier over here that the derivative of f of x is the other f of x, so you can use reverse chain rule to integrate this into big F of x squared. So that's everything we wanted to have. So now we get g of x, and then big F of x squared, and that is between 0 and 1, and then this other integral here, g prime x f, I don't really need two brackets, do I? F x squared. Okay, this is good. All we need to do now is evaluate this left expression here. So what you need to really think about is what f of 1 is and what f of 0 is. So if we go back to our little diagram that we had earlier, so we know that f of 1 is the area of underneath the entire probability distribution. Sorry, probability density function. So we know that the total probabilities of just any event would have to sum to 1. So that essentially means the area underneath the probability density function has to equal 1. And as such, that probability density function ends at 1, so we get f of 1 equals 1. Similarly, at 0, there is literally no area under the curve. So you can say f of 0 equals 0. So yeah, f of 1 equals 1, f of 0 equals 0. And now we can evaluate this. So if we put 1 into here, then that's 1, so we just get g of 1. And then if we put 0 in, then that 0 sort of cancels everything out. So now we're left with g of 1 minus integral between 0 and 1, g prime x, f of x squared. Hooray! That's that part, nice and complete. Now we've got another sort of shift in tone with this. We've got another continuous random variable y. Its probability density function is pretty similar to what we were working with in the previous part. So we have some function times big F of y times little f of y, and f and f are as above, and we want to determine the value of the constant k. With this, we can sort of work with what we were talking about earlier. So the total area underneath the probability density function is 1. So if we integrate this probability density function here and set it equal to 1, then we should be able to get a value for k. So let's get going. So first things first, there's a minor difference between what we were working with in the previous question and this. You see we have k here, but previously we had 2g of x. So that's fine. We can just say that 2g of x equals k, and then for all x. So 2g of x equals k for all x. So now we can use what we had previously. And now quickly, because we see that in our answer we're going to have to use g prime of x, we're going to quickly talk about what the derivative of this is. So we take the derivative of both sides with respect to x. We have a constant on the right, so this just becomes 0. So for all x, the derivative of g of x is 0. So yeah, we have our integral as before, 2gx, and then, yeah, what was the rest of our probability density function? Yeah, big F of y, little f of y. So I suppose I might as well put y here. However, it's important to note that this variable does not matter, because we have bounds of integration here. These functions are the same as before, so whatever variable I'd like to use, it does not matter. So this is the same. If I put x's here and did this with respect to x, we'd have the exact same result, right? So with that, we learned from the previous part that this can be written as this following form over here. So we get g of 1 minus this integral, g prime of x, and then f of x squared. Okay, first of all, what is g of 1? Well, we said that g of x is k for all of the x's. So g of 1 would just be k over 2. And we see here that g prime of x is 0, so we have this integral of 0, which is just 0. So we just have k over 2. And we said earlier that the integral should be equal to 1, because the total area under the curve should be 1. So I'm going to say 1 equals k over 2. And as such we get k equals 2. So that's that. Nice and nice. Determine the value of the constant k. Okay, that's what we just did. Part B. Show that... Okay, that looks pretty horrible. Yeah. Okay. We have an expected value, and we have to show it's between two bounds. Oh, and then we have m from the first part as well. Okay. This is interesting. First, let's talk about the expectation value. So, let's just talk about... Hang on, let's go back to the question. Yeah, we're giving this other definition here, so we want to use that answer in terms of the expectation value of x to the power of n plus 1. First, let's talk about x to the power of n plus 1. Because this had the probability density function of x was just little f of x. So this is nice to work with. So this is equal to the integral between our bounds 0 and 1 of x to the power of n plus 1 multiplied by the probability density function. In this case, it was f of x. Okay, so now we've got that in mind. Let's think about what was our middle term here. We had expectation of y to the n. So y to the n. We can say sort of the exact same thing. So we have this integral here, y to the n times the probability density function, which was k f of x f of x. I know that k is 2 now, so you have 2 f of x f of x. And I should be writing y here, so I'll do that. 2 f of y dy. So yeah, that's that. Now, let's have a think. If we go back to our very start, the very start, we have this expression here that we showed. That the cumulative distribution function is less than or equal to mx for all x between 0 and 1. So we can start forming an inequality based on this. So we can... Oh, that's not what I'm going to do. So we can say that f of y is less than or equal to m of y. F of y is less than or equal to my. So now we can say e to the yn is less than or equal to, and first of all I should probably say why we can even say this, right? So if f of x is greater than or equal to, rather I should say less than or equal to in this case, if f of x is less than or equal to g of x, this is just for not the same functions we're talking about here, but just like any functions in general, then the integral between a and b of f of x is less than or equal to the integral between a and b of g of x. And this has to be true for all x. So you sort of think about this as sort of just so we take this graph here, let's say, you know, that's f of x. Then we have, I don't know, that's g of x. This area under here is always going to be bigger than, you know, the area here, because it's negative as well. And this also works if it's negative as well, because you see that, for example, in this area here, this has, you know, I mean, actually, I realize I should probably swap these around. That should be f and g. So that's g, that's f. You see that g of x has less, you know, negative area than f of x. So it's still true when a and b are negative. So, or rather, if the functions are negative. So I guess that's sort of that. So now we can confidently say that this integral is less than or equal to, and we replace f of y with my. So we have 2my f of y dy. Okay, we can shuffle this about with it. So we can take out the 2m. We have 2m integral between 0 and 1. And now we've got a y times y. Sorry, y to the n times y. So we get y to the n plus 1 f of y dy. Okay. Now, what did we say like 2 milliseconds ago? Yeah. This integral here is fundamentally the same as this one up here. So the only difference here is that we have an x instead of a y. As we said, this variable this variable does not matter because we are integrating between bounds. We can put whatever variable we want because it's just a dummy variable. So this here is just equal to e to the x n plus 1. And we were given some sort of like variable for that. Where is it? Yeah, mu n plus 1 equals e to the x n plus 1. So this is less than or equal to 2m mu n plus 1. And then we have e y n. Okay. And yeah, you can see that that's the right hand side done. Now we've got this beautiful left hand side to think about. So let's think about this expectation value again. So we have e y to the power of n, and we had that integral from before. So this was, yeah, y to the n times 2 f of y big F of y dy. Okay, so how about we go ahead and do our integration by parts little thing that we came up with. So here our function g of x is y to the n, g prime of x. Rather, I should probably write y here. Well, I should write y. G prime of y. That would be n to the power, n times y to the power of n minus 1. So now what do we have? So it was g of 1. So this is just 1 to the n. That's just 1. Minus, and then we'll just have this integral here. So we'll have n minus 1, and then what was that little formula saying? F of x squared. Okay, this will be f of y squared. Okay, so let's look at what we're aiming for. So okay, we've got a 1. It's got 2 more terms here, so I think we'll probably have to use integration by parts again somehow. And we've got the m as well. So this m has currently made a return. So I suppose, and we notice that this is an m squared, so we can't replace big F of x with just m squared. So if we try to replace just one of them, and then try integration by parts, so we have 1 minus, rather I should say that this integral here is less than or equal to this integral here, n minus 1, and then we replace f of y with my, and then we got this dy. Okay, so now we can try integration by parts here. I guess we can clean this up a little bit first. So we have big M on the outside, and then those y's multiply, so we get ny to the n. And I guess I can take the n out as well. So we have mn. So we have y to the n, f of y, dy. Okay, so we saw we had n plus 1 terms, so if we integrate this thing and then differentiate that thing, because you know the derivative of that is the probability density function. So you say u equals f of y, then u prime would be little f of y. V prime is y to the n, v equals y to the n plus 1 over n plus 1. Okay, so now we have the following. So f of y, y to the n plus 1 over n plus 1, and then subtracted by 1 over n plus 1, and then this integral here. So it's just y to the n plus 1 f of y. And you can immediately see that this integral here, as we said not too long ago, is e to the power of x to n plus 1, which is mu n plus 1. So wrapping this all together, we get... Okay, I forgot to put this little thing here. That's between 0 and 1. We don't want to keep the f of y in our expression. And we said before that f1 is 1, f of 0 is 0. So plugging in 1 here, we just get mn, and then that's just 1 over n plus 1. So 1 over n plus 1 minus 1 over n plus 1, and that's just mu n plus 1, as we said. Okay, so that's that. So we're in a good position here. So now we have... So this expression is less than the one we just got. So as a result, we will get the expectation value of yn is greater than or equal to, we have 1 minus all of this. So we have 1 minus, and just expand out as well, 1 minus mn over n plus 1 plus mn over n plus 1 mu n plus 1. And is this what we wanted to get? Let's have a look. Mn over n plus 1 mu n plus 1. Yeah, that's precisely it. So there we go. That's that part done. So I guess writing it all out nice and neatly. Actually, I believe it was this. The way they wrote it. N plus 1 minus mn over n plus 1. This does not look like an n. Is less than or equal to expectation value of y to the n, less than or equal to, I don't even remember what this was. It's like 2m mu n plus 1. Yeah, 2m mu n plus 1. Perfect. Perfect. So we're nearly done. We just have that little part at the end left. Hence show that for n is greater than or equal to 1, then mu n is greater than or equal to that. Okay, so you see here in the previous part, by previous I mean the one we just did, we have n is greater than or equal to 0, but here n is greater than or equal to 1. So I'm thinking we could just sort of shift the indices down a bit. So if we sort of treat all n's as n minus 1 and all n plus 1s as n, then it's essentially the same as saying it's greater than or equal to 0. So we go back down here. You can see in this question, the expectation value thing just sort of disappears. So we can sort of get rid of this bit here. So now we can just say 1 plus mn over n plus 1 mu n plus 1 minus mn over n plus 1 is less than or equal to 2m mu n plus 1. So we're going to shift the indices down. We can say we send n plus 1 to n. So now we have, for n is greater than or equal to 1, we have 1 plus, and then that becomes n minus 1, that becomes n, mu n minus m, like same thing, n minus 1 over n, is equal to, and then 2m mu n. So first I'm going to times everything by n, so we get n plus m n minus 1 mu n minus m n minus 1 less than or equal to 2mn mu n. Okay, so we wanted to get mu n on its own, so we just bring that to one side. 2mn mu n plus, and then we can expand this bracket out as well. So we have plus mn, actually this is a minus actually, oops, minus mn mu n, then that would be plus m mu n. And then that is all greater than or equal to n minus mn plus m. I could probably just leave that factorized though. N minus 1. Alright. So yeah, we can see that sort of these terms just collect together. So we have mn mu n. So I guess we might as well get started factorizing this out. So we get mu n, and then what do we have on the outside? We just have mn and then plus m. Okay. And that's greater than to n minus m, n minus 1. Okay, so I guess factorizing that out again, we'll get m, n plus 1. Oops. Pressing to n minus m, n minus 1. Nearly there. Then we just divide both sides by mn plus 1. And since n is positive and m will be positive as well, that inequality sign won't flip. So we have mu n is greater than or equal to, we just have n over mn plus 1 minus, and then those m's cancel out here, so we have n minus 1 over n plus 1. And there you go. That is what I believe they asked us to show. I'll just quickly look. Yeah. Nice.